and not repeating unnecessary work.
And it's not just for cutting rods. Dynamic programming is used all over, from finding the shortest path in a graph to aligning DNA sequences. It's a really versatile technique.
Okay, so it's about breaking things down, remembering the solutions, and building up the answer from the bottom up.
You got it. All right, ready for chapter 15. It's all about greedy algorithms.
Greedy algorithms, that sounds kind of selfish.
Haha. Well, they're not really selfish, but they do like to make the best choice at each step, hoping it will lead to the best overall solution. It's like planning a road trip by always choosing the shortest route to the next city.
That sounds reasonable, but what if the shortest route isn't the best way to get to your final destination?
That's the thing. Greedy algorithms don't always guarantee the optimal solution. Sometimes you can get stuck in a local optimum and miss the bigger picture.
So it's like taking a shortcut that ends up being a dead end.
Exactly. The chapter goes into the details of when greedy algorithms work well and when they don't. It talks about the greedy choice property and optimal substructure, which are the key concepts to understanding these algorithms.
Okay, so it's about knowing when greed is good and when it's better to be more strategic.
Exactly. And the chapter gives some cool examples, like Huffman coding for data compression and Kruskal's algorithm for finding minimum spanning trees in graphs.
Sounds like they're good at finding those efficient solutions.
They can be. Okay, chapter 16, we're getting into amortized analysis.
Uh-oh, another one of those intimidating terms. What's that about?
It's not as scary as it sounds. It's a way of analyzing the average cost of operations over a sequence of operations. It's like budgeting for a month, instead of stressing about every single purchase.
So instead of looking at the worst case for each operation, we're looking at the bigger picture, the average cost over time.
Exactly. It helps us to smooth out those fluctuations in cost and get a more realistic picture of how efficient something is.
Can you give me an example?
Sure, think of a dynamic array. It's an array that can grow as you add more elements.
Okay, so like a list that expands automatically.
Yep. Most of the time, adding an element takes constant time. But every now and then, when the array gets full, you have to resize it, and that can take longer.
So those occasional resizings could skew our understanding of the array's performance if we just focused on the worst case.
Exactly. Amortized analysis helps us take those resizings into account and show that, on average, the cost of adding an element is still pretty good.
So even though there are occasional spikes in cost, the overall performance is smooth, like having to buy groceries once a week, but the cost of food per day is still manageable.
Perfect analogy. And the chapter goes into different methods for doing amortized analysis. It's pretty clever stuff.
Okay, so it's about getting the real picture, the long-term average cost.
Exactly. All right, on to chapter 17. Augmenting data structures. Now we're giving those data structures some upgrades.
Upgrades, like adding turbochargers to our linked lists.
Haha, kind of. Augmenting a data structure means adding extra information or functionality to it without messing up its basic properties.
So like adding GPS to your car without changing how the engine works.
Perfect. The chapter focuses on red-black trees, which we talked about earlier. It shows how you can add extra fields to the nodes to track things like the rank of a node or how many nodes are in its subtree.
Okay, so it's like keeping statistics about the data, in addition to just storing it.
Exactly. It can be really useful for certain applications. Like, imagine you're managing a leaderboard for a game. You might want to quickly find the player with the 10th highest score.
That's a good point. Without those extra stats, you'd have to search through the whole leaderboard.
Exactly. And by augmenting the red-black tree, you can do those kinds of searches very efficiently.
So we're not just storing the data, we're adding intelligence to it.
And the key is to do it in a way that doesn't slow down the original operations of the data structure.
Right. We don't want those upgrades to backfire and make things slower overall.
Exactly. Okay, chapter 18. Time to talk about B trees. Now we're getting into some serious data management.
B trees, what are those all about?
They're designed for external memory systems, like hard drives.
Okay, so like when you're dealing with huge data sets that don't fit in the computer's main memory.
Exactly. Accessing data on a hard drive is much slower than accessing it in memory, so you need special data structures to minimize those slow disk accesses.
It makes sense. We want to avoid those bottlenecks.
And that's what B trees are good at. They're balanced search trees, like red-black trees, but they can store multiple keys per node.
So it's like a multi-level filing cabinet, where each drawer can hold multiple files.
That's the idea. It reduces the number of times you need to access the hard drive, which makes things much faster.
Okay, so B trees are all about efficiency when you're dealing with massive amounts of data.
Exactly. They're used a lot in database systems and other applications that handle lots of data. All right, Chapter 19, it's all about data structures for disjoint sets.
Disjoint sets. That sounds kind of abstract. Can you give me a real-world example?
Sure, imagine you're managing a social network, right? And you want to keep track of different groups of users.
Like communities or something.
Exactly. Disjoint set data structures let you efficiently manage those groups. You can create new groups, merge groups together, and quickly check if two users are in the same group.
So it's like having a dynamic map of all the connections in the social network.
That's a great way to put it. The chapter goes into the specific operations you can do on these sets and how to optimize them. It gets into some cool techniques like
Oh.
union by rank and path compression.
Okay, those sound pretty technical.
Yeah,
But the gist is that they make managing those groups much faster.
exactly. Now, let's jump back into the world of graphs, but this time with a focus on algorithms for exploring and analyzing them.
Graphs. So we're back to those networks like social networks or the internet.
Exactly. Chapter 20 focuses on breadth-per-meters search and depth-first search, two fundamental algorithms for graph traversal.
Traversal meaning like exploring the graph.
Yep. These algorithms are like explorers mapping out the territory of the graph.
So they're helping us understand the structure of the graph, how everything is connected.
Exactly. Breadth-first search explores the graph layer by layer, starting from a chosen point and visiting all its neighbors before moving to the next layer. Depth-first search, on the other hand, delves deep, exploring as far as possible along each branch before backtracking.
So it's like exploring a city, either by visiting every building on each block before moving to the next block, or by following one road as far as it goes.
That's a great analogy. And these algorithms have tons of applications, like finding the shortest path between 2 points or identifying clusters of connected nodes.
Okay, so they're powerful tools for understanding networks.
Absolutely. And in chapter 21, we get into minimum spanning trees. Imagine you want to connect a bunch of cities with roads, but you want to do it as cheaply as possible.
So we're optimizing for cost.
Exactly. A minimum spanning tree gives you the cheapest way to connect all the cities without creating any loops.
Okay, so it's the most efficient way to connect the dots.
Exactly. The chapter presents two classic algorithms for finding these minimum spanning trees: Kruskal's algorithm and Prim's algorithm.
Two more algorithms to add to our collection. Do they both use that greedy approach we talked about earlier?
They do, but they go about it in different ways. Kruskal's algorithm starts with a bunch of individual cities and gradually adds roads, always choosing the cheapest one that doesn't create a loop. Prim's algorithm starts with one city and keeps adding the cheapest road that connects to a city that's already a part of the tree.
Okay, so they're both greedy, but they have different strategies.
Yep, and they both guarantee finding a minimum spanning tree, but one might be faster than the other depending on the specific network of cities.
It's like choosing between different construction companies. They both get the job done, but one might be better suited for a particular project.
Great analogy. Now, chapter 22 takes us back to shortest path algorithms, but this time we're finding the shortest path from a single source to all other destinations in a network.
So like finding the best route from your house to every other point in the city.
Exactly. The chapter covers Bellman-Ford algorithm and Dijkstra's algorithm, two powerful algorithms for solving this problem.
Okay, two more algorithms to keep track of. What's the difference between them?
Bellman-Ford can handle situations where some of the connections have negative weights, like if you're factoring in tolls or traffic delays. Dijkstra's algorithm is more efficient, but it only works if all the weights are positive.
So it's like choosing between different navigation apps, depending on whether you want to avoid tolls or just find the fastest route.
Exactly. All right, chapter 24. Now we're getting into flow networks. Imagine a network of pipes carrying water or a transportation network with roads that have different capacities.
So it's about managing the flow of something through a network, considering the limitations of each connection.
Exactly. The goal is to find the maximum flow that you can send from a source to a sink in the network.
So like maximizing the amount of water flowing through the pipes, or the number of cars that can travel on the roads.
Yeah. And the chapter introduces the Ford-Fulkerson method, a classic algorithm for finding those maximum flows. It uses the idea of augmenting paths, which are paths through the network that have extra capacity.
So it's like finding those back roads that can help you bypass traffic jams and get more cars to their destinations.
That's a great analogy. And there are different variations of this method, like the Edmonds-Karp algorithm, which improves the efficiency by choosing those augmenting paths in a clever way.
Okay, so it's about finding the best strategy to maximize the flow.
Exactly. All right, on to chapter 25, which is all about matching problems in bipartite graphs.
Bipartite graphs. Those sound familiar, but remind me what they are again.
They're graphs where you can divide the nodes into two groups, and the connections only go between those groups, never within a group.
Right, I remember now. Like a dating app where you have a group of men and a group of women, and the connections represent matches.
Exactly. And a matching problem is about finding the best way to pair up those nodes, like
Hmm.
how to match the men and women to maximize.
So it's like playing matchmaker, but using algorithms to find the optimal pairings.
That's the idea. The chapter introduces the Hungarian algorithm, which is a classic algorithm for solving these matching problems. It's used in a lot of different areas, like assigning tasks to workers or finding the best pairings for organ transplants.
Wow, so those bipartite graphs and matching algorithms are a pretty wide range of applications.
They do. Okay, chapter 26. Now we're getting into the world of parallel algorithms. This is where things get really exciting.
Parallel algorithms, so we're talking about using multiple processors to solve problems faster.
Exactly. With modern computers having multiple cores, it's becoming more and more important to be able to harness that parallel processing power.
It's like having a team of workers tackling a problem together, instead of just one person doing everything.
That's the idea. The chapter introduces the fork join model, which is a way to divide a problem into smaller tasks that can be solved concurrently.
So you split up the work, do it in parallel, and then combine the results at the end.
Exactly. And it gives some examples like parallel merge sort and parallel matrix multiplication. It also talks about speed up, which is how much faster the parallel algorithm is compared to the regular one.
So it's about measuring how much benefit you get from using multiple processors.
Exactly. Okay, on to chapter 27. This one's about online algorithms.
Online algorithms, does that mean they work on the internet?
Haha, not exactly. It means they have to make decisions as data comes in without knowing what's going to happen in the future. It's like playing a game where you don't know what your opponent's next move will be.
That sounds challenging. So they're kind of improvising as they go.
In a way, yeah. The chapter gives examples like caching algorithms, where you have to decide what data to keep in a cache, even though you don't know what data will be needed next.
So it's like managing a library, right? You have to decide which books to keep on the shelves and which to put in storage, even though you don't know which books people will want to borrow next.
Exactly. And it talks about how to analyze these online algorithms using something called the competitive ratio, which compares their performance to an algorithm that knows the future.
So it's about measuring how well they do, even though they're working with limited information.
Exactly. Okay, we're getting close to the end here. Chapter 28 is all about matrix operations. Back to those grids of numbers.
Yeah, those matrices. I remember struggling with those in math class.
Well, they're actually pretty important in computer science. They're used all over, from graphics and image processing to machine learning.
So they're not just abstract mathematical objects, they actually have practical uses.
Absolutely. The chapter covers things like matrix addition, multiplication, and transposition, which are the basic operations. It also gets into Gaussian elimination, which is a way to solve systems of linear equations, and LU decomposition, which is a way to break down a matrix into simpler parts.
Okay, so it's giving us the tools to work with those matrices efficiently.
Exactly. And chapter 29 takes us into linear programming. This is a powerful technique for optimization.
Optimization, meaning like finding the best solution to a problem.
Exactly. Imagine you're running a factory that makes different products, and you want to figure out how to maximize your profit given your limited resources. That's a linear programming problem.
Okay, so it's about finding the best way to allocate resources and make decisions to achieve a specific goal.
Exactly. And the chapter gets into how to model these problems as linear programs and different algorithms for solving them, like the simplex method.
Sounds like it could get pretty complex.
It can, but that's a great way to put it. And this efficient switching between representations is what makes the FFT so powerful. It's used in signal processing, image analysis, even cryptography.
Okay, so it's one of those hidden heroes of the digital world, quietly working behind the scenes to make things work better.
Exactly. All right, last chapter. Chapter 31 takes us into the world of number-theoretic algorithms.
Number theory. That sounds pretty abstract. Is that even useful in the real world?
It is. It might seem far out, but number theory is actually the foundation of modern cryptography, which is what keeps our online transactions secure.
Wait, seriously, so all those online shopping sprees I do are protected by ancient math?
Pretty much. The chapter goes into the basics, like prime numbers, divisibility, and modular arithmetic. It even covers the Euclidean algorithm, which is thousands of years old.
Okay, so even though it's old, it's still relevant today.
Oh, yeah. Those concepts are the building blocks of modern encryption algorithms. It's what keeps our data safe from prying eyes.
So it's not just about abstract math. It's about protecting our privacy and security in the digital age.
Exactly. And the chapter goes into some more advanced stuff like Fermat's Little Theorem and Euler's totient function, which are used in things like public key cryptography.
Okay, so it's those fundamental number theory ideas that make all that modern security possible.
Exactly. And that brings us to the end of our algorithmic journey. Welcome back for our final deep dive into algorithms. We've explored so much already, but there's still more to discover.
Yeah, we were just talking about those advanced string matching algorithms in Chapter 32, like Raben-Karp and Knuth-Morris-Pratt. They're all about finding shortcuts, right?
Exactly. We don't always need to check every single character. Raven-Karp uses hashing to quickly compare chunks of text, kind of like creating a fingerprint of the pattern we're looking for.
So it's like those crime shows where they compare fingerprints to eliminate suspects.
Exactly. And Knuth-Morris-Pratt, well, it analyzes the pattern itself to figure out how to skip ahead when a mismatch happens.
So it's like navigating a maze. If you know the layout, you can avoid those dead ends.
These algorithms are everywhere, from spell checkers to search engines. They make our digital lives so much easier.
It's amazing how these seemingly small things can have such a big impact. Well, we've reached the end of our algorithmic journey. It's been quite an adventure.
We've seen how algorithms are the building blocks of so much of what we do with computers, from sorting data to finding the best route to encrypting our messages.
We started with simple sorting and ended up exploring some pretty complex stuff like dynamic programming and cryptography. It's been a whirlwind tour of the algorithmic world.
And I hope our listeners have gained a new appreciation for the power and beauty of these computational marvels.
Algorithms are everywhere, working behind the scenes to shape our digital experiences.
Understanding them gives us a deeper appreciation for how technology works and how we can use it to solve problems and make a world a better place.
Thanks for joining us on this deep dive into algorithms. We hope you've enjoyed the journey as much as we have.
And remember, keep exploring, keep learning, and keep those algorithmic gears turning.
Until next time.